question for this unit is, do you think it is possible to have an earthquake in Mississippi? So whenever we're looking at Mississippi, right now we do not have an actual fault line near us, but we do have what we call the New Madrid fault line directly north of us in Tennessee. This fault line is the second most active fault line in the United States.
The first earthquake occurred around 2 a.m. on December 16, 1811 in northeastern Arkansas. Estimates place the magnitude of this earthquake around 8.1, and it was followed within hours by another shock nearly as strong as the first. All through the night the region was shaken. When dawn brought light, the townspeople found the air clouded by a reddish haze, and the landscape changed forever. In the following 2 months, the region would experience 3 more major earthquakes and almost 2,000 aftershocks. On January 23, 1812, another shock, estimated at 7.8, occurred. As people stumbled into the night, they saw flashes of light emanating from the ground. Many found themselves navigating through fallen trees, wading through sand and water, or stumbling into crevices that had opened in the ground. The Mississippi River rocked back and forth, tossing boats onto shores which themselves were crumbling into the river. It was nothing short of a living nightmare. On February 7, 1812, the strongest shock yet rocked the town of New Madrid so violently that it finally fell away into the river, joining the fates of several other settlements. The river itself ran backwards, and in Tennessee a great forest suddenly became a vast lake. The ground was seen rolling like the swells of an ocean. When the swell peaked, great fissures opened in the ground, some of them running for hundreds of feet. 1,300 miles away in Boston, Massachusetts, church bells rang out in response to the shaking, and in Washington, D.C., James Madison, the sitting president of the United States, was awakened from his sleep while the White House.
So whenever we're looking at this, the New Madrid fault line is only in most actively right here. However, this is the level of intensity that we have. However, it also spreads all the way around. So whenever we look at this fault line, the question comes up of, do you think we can have an earthquake where we're located at in Mississippi, which is only a very short distance between the fault line and us. The first time it had an earthquake, you could feel it all the way over in D.C., this distance. So more than likely we could. So since we're on this map, let's look over here at California. California does have the most active fault line in the United States. Our fault line, the New Madrid fault line, is only the second most active that we have. This whole concept ties into what we call plate tectonics. Plate tectonics first was looked into by a man named Alfred Wegener. He came up with an idea that we call continental drift. All that talks about is the continents drifting from their previous location to where they are now. Their previous location we call Pangea. All Pangea is the large landmass where we were all connected at one time. So whenever we look at Pangea, we have interactive plate tectonics on this website. So to see our animation, let's look here. Now this is over the course of thousands of years. We went from Pangea to where we are currently located. So the question here says, today the continents are still in motion. What is causing these continents to move? We have a concept called plate boundaries. Now, our plates that we see move due to certain evidences. We can see that they move because we have very active boundaries right through here. A boundary is just where two different tectonic plates meet. Where they meet and they're moving a lot, that's an active boundary. Now in 1960, Harry Hess took Alfred Wegener's idea of continental drift and built upon it to come up with a topic called seafloor spreading. Seafloor spreading is just as it says as well. It's about the seafloor actually spreading apart. Now all he did was built upon this concept, and he proposed, so he suggested that hot, less dense material below Earth's crust. Now the crust is what we walk on. The hot, less dense material below Earth's crust rises towards the surface at what he called a mid-ocean ridge. Let's look into first the word hot. We know heat rises. Then less dense means less packed molecules, which is also going to rise. So it's going to rise towards us, away from the core, at what we call a mid-ocean ridge. This is just a part in the ocean where the land separates. It can actually occur at a mid-ocean ridge, which is in the water, or it can also occur on land. Now, whenever we look at all this idea and we combine continental drift and seafloor spreading together, we get the entire theory of plate tectonics. Plate tectonics is when Earth's crust and the upper mantle are broken into sections. These sections we call plates. An entire plate is like the Eurasian plate right here, or the North American plate. This entire part is a plate. Now, these are broken into different sections. These sections actually correlate directly with the continental names that we have. So, Arabia is on the Arabian plate. India is on the Indian plate. Africa is on the African plate. South America on the South American plate. The Caribbean islands on the Caribbean plate. And so forth. Philippines, Eurasian with Europe and Asia. Now, whenever we have these, the tectonic plates that we're looking at are split into actually two different main layers. The first layer is the lithosphere. This is the layer that's on top. It contains the crust and a part of the upper mantle. So right here, here is our crust, and here is our crust. Now this part is your upper mantle. This entire layer right here is your lithosphere. Now directly underneath your lithosphere is your asthenosphere. This is the plastic flowing part. Whenever we're looking at layering the earth, we need to work from the inside out to fully understand the concept of the earth. So the very first layer that we have is the inner core. The inner core is a solid material because we have a bunch of pressure on the outside of Earth moving and pushing into the Earth, compressing all of these molecules to make them look and make them act as a solid. Now, as we work our way out, the next layer that we have is our outer core. The outer core, since it's not as compressed, since we're moving outwards, it's not that compressed, therefore it is a liquid. When we work our way out, the next layer, which is actually from here to here, is your lower mantle. After that, you have from here to the outer part, this is your upper mantle. The lower mantle plus the upper mantle is called just the mantle. Now what we're going to look at is a tiny portion which entails this part right here. Whenever we're looking at this, we left off one tiny part. We have our crust, what we actually walk on. This is the oceanic crust. Which makes up all of your oceans. This part is your continental crust. It makes up all of your land masses. Whenever we look at this tiny little layer here, we are looking to create our boundaries and how our boundaries actually interact. Now, an easy way to remember this, your lithosphere is above your asthenosphere. So think of the Los Angeles symbol, LA. Lithosphere first, then the asthenosphere comes afterwards. Now, whenever we're looking at this one, this is a diagram of this small section right here. So what we're looking at is, first of all, we have our ocean. Underneath our ocean, we have a crust, which is what we actually walk on. This is called the ocean crust. Now, over here, we have continental crust. This is what the land masses are made up of for the different continents. Now, whenever we're looking at this, we have oxygen up here, we have H2O right here, both pressing down. So the oceanic crust is going to be more dense than the continental, because the continental only has oxygen pressing down on it. The oceanic has oxygen and water pressing down, so this one is less dense. So now if we move down from the crust we know, since we walk on it, it's a solid. As we move down towards the core, the heat from the core melts some of that solid material and creates our upper mantle, which is rigid. The upper mantle we call rigid because it is part solid and part liquid. It's like a bucket of blocks. It's solid and it hurts, but yet you can still pour it out and make a pile of stuff. So since the upper mantle is rigid, what we have is we have solid, solid plus liquid, and then as we move down, this is going to be entirely liquid. Until we get closer to the core, which is solid. So again, this is going to be liquid, but still rigid for the lower mantle. So we call it semi-rigid. Now, remember your symbols, L, A. Since the lithosphere is on top, and it's what we walk on, it contains the crust. So the crust plus the upper mantle is your lithosphere. Directly beneath the lithosphere, you have your asthenosphere, which is right here. So let's look at this one last time. Your lithosphere is your crust plus your upper mantle. Directly beneath your lithosphere is the asthenosphere, which is liquid and flowing. Now, because of this, we have borders between these plates that we're creating. A border between tectonic plates is called a boundary. We have 14 major boundaries in the world. These boundaries honestly compose our oceans and all of our continents. That's either going to be continental crust or oceanic crust. If a continent is on it, it is continental. On the contrast, the Pacific plate makes up only the Pacific Ocean. So it is an oceanic crust. While the North American plate has North America on it, it is a continental crust. Meaning the Pacific plate is more dense than the North American plate, because this is oceanic, this is continental, and oceanic is always more dense because it has oxygen and water pressing down on it. Now the question comes up, what causes our tectonic plates to move? We know about the plates, we know about the layers of the earth, but we now need to look at what actually causes these plates to move. We have, within our theory of tectonic plates, we have the idea of convection currents. A convection current, all it really is, whenever you talk about a convection current, think of weather. What a convection current is when heat rises and then cold air sinks. That's a convection current in summary. Now, whenever we look at a convection current occurring in the mantle contains magma. So whenever we look at this, we have a hot, less dense. So if it's hot, it rises. Less dense, so my molecules are further apart. Plastic-like rock that moves away from the core, because so if it's moving away from the core, what we have is, here's the core. If it's moving away, it rises to the surface, because remember, heat rises. Then once it gets up to our plates right here, it hits the cool air. It condenses to make it nice and cool, and we know cold sinks. It makes it dense, so they are closer together, the molecules. At this point, they move toward the core, which means they move down. So once they get nice and hot, they'll cycle through. And like right here, nice and hot, it starts to get cold, and so it sinks. Because what we walk on is the crust, which is cold. It's still the concept of a convection current. The only thing that's different now is that we're looking at magma heating up, rising, cooling off, and sinking instead of just air molecules. The molecules still act the same. If it's hot, they're further apart, so they rise. If it's cold, they're closer together, so they sink. The only thing that's different is that we're looking at magma instead of oxygen.
But the huge molten core contributes something else essential for life on Earth. A way of helping to regulate the planet's temperature. It's a remarkable system. Magma, heated by the core, rises towards the Earth's surface. As it spreads sideways, the Earth's crust is very slowly dragged apart. This moves the continents, creating the Earth's restless and ever-changing surface.
So now what we're looking at, if you saw on that video, the convection current with the magma is what was rising. As it rose and cycled away from each other, you should have noticed that the tectonic plates, the outermost layer, was being pulled along with it. So whenever we're looking at this, there's a few key things that you need to understand about convection currents. Convection currents are massive, just like air mass movement. If you remember when I talked about air mass movement being from the equator all the way up, not just over a single little state, it's the same idea. The convection currents are actually thousands of kilometers wide. This is the part that you need to know. They're thousands of kilometers wide, but they flow at very slow rates. They only flow at a rate of a few centimeters per year. We believe, and I say we as in scientists, and right now, everybody, we believe that that movement, the few centimeters per year, that cycling movement you saw in the video, is what makes our plates of the lithosphere, which is our crust, actually move. Now let me go ahead and say this. We know our crust moves. We have earthquakes. We can measure the distance of one house on one side of an earthquake and a house on the other side of the earthquake and see that they have shifted afterwards. We can measure the height of mountains, and we see that mountains get taller after tremors or different things like that. After volcanic eruptions, we can see that things are getting closer together on either side of the volcano, but we've got to figure out why the convection currents cause all of this. So whenever plates actually interact, they can interact in three main ways. The first way that we have is by separating. When they separate, it looks like this. You see your two arrows going away from each other. It's a simple concept. Now, as this part separates, this is one whole lithosphere right here. As it separates, it's moving this way. So this part is diverging, which is this one, separating. As it diverges, it also collides with a different plate on the other side of that boundary. So we have our second one, which is colliding, which we call convergent boundaries. Along with convergent boundaries, we have places where we have cracks, where they are sliding past one another. This is what we call a transform boundary. Boundaries never occur alone. If it is diverging at one part of the plate, the opposite part of the plate is doing something else. So if it's separating at one part, it's more than likely coming together on the other side. Now, if we have boundaries that are very active, we call these fault lines, just like the fault line that we have in Tennessee, the New Madrid fault line. These are just some pictures to show you what a fault line would actually look like. So right here, one plate moved this way, another plate shifted this way to give us this crack. And you can see where they're not lined up anymore for the crops. Also write this top picture. This top picture is a picture of the side of a cliff. Right here is the bottom. So what happened here is it moved this direction, and whenever it shifted to the right, the cliff that was already there fell and broke into different pieces, giving us these big long cracks. Now this boundary is in California. This boundary is shifting side by side as well, and as it shifts, it crumbles, almost like toast crust crumbling together. It crumbles and creates our mountains on either side of this boundary. Watch the video. We have heat rising. As it rises, it spreads apart. As it spreads apart, it pulls this along with it. When it does that, you have magma that bubbles up, fills in the crack to create new crust. The act of it cycling away from each other, see how it's going away, is called a divergent boundary. A divergent boundary diverges, which easy way to show this is show two arrows going away. So it's like you divide. Whenever you divide, you separate. And that's what we're doing. We are separating the two layers that we have. The reason we have the divergent boundaries is because we have rising material Now this material we call magma. We have rising material or magma in a convection current. The convection current occurs within the asthenosphere. So the convection current rises, it rises up, it spreads out, and as a result, it pulls the plates out with it to leave a little crack in the surface. This crack is then filled in with new magma to give us our new crust. So here are just some pictures of how divergent boundaries actually form. They first start off like this. Just a crack in the surface, and you can even see some of the smoke still coming up. They then move into this part having some water still, making a little river. And eventually they move into this picture. This is a picture of a bridge between two different continents over in Iceland. This is the bridge that connects Iceland to the UK. So whenever we have divergent boundaries is where they move apart. So we can draw, just as a little summary, arrows going away. As they separate, as these plates separate, we get long cracks that we call rifts. This is a rift. It's just a crack. So watch this video. It comes up, it cycles away. As it's cycling away, you have your magma erupting on the surface. This magma then solidifies to give you these ridges, which are the new crust. So the first one we have is an oceanic divergent boundary. So first of all, up here, above the water, we have oxygen molecules pressing down on the water. Then right here, we have water molecules actually pressing down on what we walk on. And it occurs in both locations. Just because there's water over here doesn't mean that there's not water pressing down over on this side. It's still the same. Now, as we press down, what we walk on right here, this is your lithosphere. Over here is the same thing. It is still your lithosphere. Now remember this symbol. Directly underneath your lithosphere, you have your asthenosphere. This is where you have your magma. Now, remember, the lithosphere is split into two different layers. Since this one is under the water, we call this one oceanic crust. Same thing over here, still under the water, so it is still oceanic crust. Now, if you remember from your chart, your lithosphere has crust plus the upper mantle. So that means oceanic crust on top, upper mantle on the bottom. So what we can do, we know this is water, so we can color this blue. We know that the lithosphere is what we walk on, so that's your brown, because that's the dirt or the sand pretty much. Now your asthenosphere is what has your magma, so it's hot and flowing. So we're going to color this entire part red. Now, whenever we're looking at this, you still have a gap right here. This gap is going to eventually be filled in with magma. But if you see this gap, what we see is if there's a gap here, that means our plates are actually separating. In order for our plates to separate, we have to have our convection currents cycling up, because remember they rise from the core. They cycle up and cycle away. As a result of them cycling away, they pull our lithosphere along with it. And this is where the two arrows going away for divergent comes into play. Your two arrows right there. Now, as they cycle up and they start to pull the crust away, you have this gap that gets formed. This gap then gets filled in with magma, and it forms new crust. So our crust overall is moving away from each other, forming new crust in the middle. Now look at this picture. This is a picture of divergent boundaries on the continent. So since we're on the continent, let's look at this. We really only have oxygen up here. We don't have air, so we only have oxygen pushing down. And again, remember, it still pushes down on both sides. We're not going to run out of oxygen just because we're on the other side of a boundary. So the first thing that we have, whenever you look at it, this whole part is still your lithosphere. This whole part is still your asthenosphere. Now, this is where you've got to remember lithosphere, asthenosphere. This is crust and upper mantle for the lithosphere. So it's broken into sections. Both of them are the same way. This one has just oxygen above it. This one has just oxygen above it. So this is a continental crust on both sides. Beneath both of these, we still have our upper mantle. Now, underneath it, we still have our asthenosphere, which is composed of molten magma. So whenever we go to color, let's first start off this time by coloring our asthenosphere red. So what happens with the asthenosphere here, since we still have this gap, anytime that you see a gap like that, and they're pretty much even across, except for right here where it rises up a little bit, we have convection currents occurring away from each other still. So they go up, they push some of this up, which is why we have this rising effect, and then cycle away. As a result of that, it still pushes our crust away from each other, giving us a gap. This gap allows for magma to come up and fill it in, forming, yet again, new crust. So look at these two concepts on your picture, on your note page. Are they really different? This one still has the crust moving away. Magma circles up and out, up and away. This one has the crust still moving out. Magma is circling up and away. The only real difference is that this one is underwater, while this one is on land. Still the same concept. So it's still diverging. It still divides. Now watch this video. This one, you saw them pointing towards one another. As they push together, it forms a hill, and every now and then it will snap, and you saw the wave go over it. That gives us a tsunami. That uprising that you saw right here, that hill formation, these are caused by convergent boundaries, meaning they come together, they converge. With a convergent boundary, that material, that magma, moves down in the current, so that means it's moving towards the core, and pulls the plates down with it, which is what we see right here. So it cycles down. As a result, it pulls the more dense plate down along with it. The less dense plate, continental, will then eventually rise up to form mountains or volcanoes or anything like that. So whenever we have a convergent boundary, we're looking at the fact that more dense plates sink. So they go down towards the core. The heat in the mantle causes the sinking and overlying mantle to melt, so then they become flowing. This is in the asthenosphere. Once it's melted within your asthenosphere, remember it's melted, so it is hot. Hot rises, so it's forced back up towards the crust. When it's forced up like this, on our Earth's surface, we get volcanoes. Now, the most famous set of volcanoes across the entire world, we call this the Ring of Fire. Look in your book on page 228 to 229 to see pictures and to read about volcanoes with the Ring of Fire. So let's look at a few examples of a convergent boundary. When we have a convergent boundary, you'll see a picture, and you will always see, for convergent, you'll usually see something sinking down or something building up. So right now, let's just start off with the basics. You have oxygen here that is pushing down. You have water here that is also pushing down. On this crust, notice the water is not pushing down on this one. It's just oxygen. Now, since this is the layer under the water, this is still our lithosphere, but this is the oceanic crust, and this is your upper mantle, while this one over here is still, again, your lithosphere, but notice how there's no water up here. So this one is called your continental crust and your upper mantle. Now remember, your continental crust, because it only has oxygen pressing on it, is less dense. Which means your oceanic crust is more dense. Now, we always know if it's more dense, the molecules are packed really tightly together, so they sink, which is why the oceanic crust will always sink when it interacts with a continental crust. This sinking motion that we see here is what we call subduction. Now, remember, lithosphere is on top, asthenosphere is on bottom. So that means we have asthenosphere here, and we have asthenosphere here. Both still containing magma. So since the magma is nice and hot and molten, it still rises towards the surface, just like in all the other diagrams. But now we've got to look at how it's going to interact as evidence of plate movement. So what we see is we have plates moving downward right here. So that means we have one convection current cycling this way. Now this plate is trying to move this direction. So we have one convection current cycling this way. So you see they converge because you have two arrows pointing towards one another, which is our convergent boundary. Now you have to remember, the more dense will always sink. When it sinks, it gets down in the magma. It's really, really hot down here, so it melts really quickly. When it melts, it goes to rise up, and this rising forces the rest of this to be pushed upward to give us mountains or volcanoes. It doesn't actually create new crust. What it's doing is it's building up down here, and the more you add down here, the more this gets pushed upward. So this is all old crust that's being forced up because the new is down here. So we don't actually see new crust at convergent boundaries like we do at divergent boundaries. So this is a concept that we have. Now, I said mountains. Most mountains have either been a volcano, are a volcano, or will become a volcano. So looking at this picture, you have right here your lithosphere, which is your crust, and the upper mantle. The convection current cycles down. It pulls the more dense, you see, is oxygen and water. It pulls the more dense down along with it. When it goes down, it melts really quick. You form a pocket of what we now call lava, which is then forced up. Now we have a convergent boundary again. This time, this is an oceanic convergence. So, start from the basics again. Oxygen, water, both pressing down. So that means both of my plates are going to be pretty dense here. Now, since they're both pretty dense and they're both underwater, they are both oceanic crust. Still within our lithosphere. Now remember, underneath your crust is the upper mantle. I say the crust, so crust, Never forget this. Crust, And then you have your asthenosphere beneath it. So whenever we're looking at this, you see the motion of one going down and one staying right here. You see that there is a volcano right here. So that means this one, since it's the one subducting, it is now the more dense layer of the two, which means this one is less dense. Now, since this one is subducting, remember all down here you have your convection current. So this is your asthenosphere. All right. Now, remember within your asthenosphere is where you have your convection currents. So, since this one is moving down, that means we have a current pushing it down right here. This is current number 1. And then we have a second current coming over here, which is current number 2, pushing this crust this way, this crust this way. Still the same symbol for convergent, coming together. What happens with this is that we have same concept. It melts so quickly, it's then forced upwards, because remember, heat rises. When it's forced upwards, it forces this part along with it and makes this rise up to give you volcanoes or also islands. And the third type of boundary for convergence is whenever a continent and a continent converge. So whenever we're looking at this, we still have oxygen pressing down. Still have oxygen over here. We didn't run out. This is still my lithosphere and asthenosphere. Now remember, the lithosphere is broken into two parts. This one is continental crust because there's only oxygen up here. Remember, crust, This one is still continental crust. And remember, crust, is upper mantle. Now what we have here is we have a random in the middle of, say, a continent. Think of like north of Tennessee or Arkansas area with mountains. We have a random little push up. Continental crust has similar densities, so none of them really subduct beneath another one, except they push up to create mountains. So now we have to figure out why they push up. So whenever we see them pushing up, that means we have our asthenosphere down here. Always have the asthenosphere. And what it is doing is that since this is moving up, it is pushing this crust towards each other. So when they push, they get larger. So that means our cycling for the convection current is towards one another. causing our plates to move towards one another, giving us a still convergent boundary. This is the concept that we're looking at. Since they're moving towards one another, they branch up and spread out to form our mountains. Finally, the last boundary that we're going to look at. This is one of the most simple boundaries that we have. This is called a transverse boundary, but you do need to know it also has another name. It's transverse, but it's also called transform. You can hear it called both. So whenever we're looking at a transverse or transform boundary, that's when the plates slide past one another, like in this image. When they're sliding past each other, we get a lot of tension. This tension is what causes our faults, which are the large cracks that we have in the crust. It's just like a piece of toast. If you toast bread and then you push and rub the two pieces next to each other, it's going to break and it's going to crumble into pieces and leave gaps. Same concept with transverse boundaries. Now let's look at this top left picture. One thing very unique about transverse and transform boundaries is that they never really occur alone. So we have, first of all, we have a divergent boundary here, 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 and here. So that means they're separating right through here. Now, you see how they're at different lengths? That's because they're separating at different speeds. So it's like multiple cars driving at all different speeds. Some are going to be ahead, some are going to be behind, some are in the middle. Whenever we look at this, you have these cracks in between where they are dividing. This crack is your transverse boundary, meaning this one's going really fast, but then this one's going really slow. The most famous transverse boundary that we have is in California. That is called the San Andreas Fault Line. What happens with San Andreas is one part is shifting one way, another part is shifting another way. So let's look at this picture real quick. This is your divergent and your convergent boundaries combined. So what we have here, our first part is a divergent boundary because it's rising up and cycling away. So it separates right here, meaning this part is moving this way, this part is moving this way. So they divide, they diverge. Now, this is one entire plate. As this plate moves to the right, it collides with this plate trying to move to the left. So right here, this is a convergent boundary. Once it gets down here and it starts to melt, it melts and then is forced back up to give us a volcano. At a continental crust and an oceanic crust. Because remember, the oceanic is more dense, so it sinks, which is called subduction. subduction. So look at these boundaries. The first part is what I want to show you right here. So this is the North American plate. I'm going to color it in blue. Now overall, the North American plate, if you look at it, is moving this away, which means it is diverging right here, but it is converging with this one. So if this entire plate shifts this way, it's separating from all of this location, but then it's colliding all the way over here. This is where California is. California is the plate that is shifting and moving. So as it moves up, this one is trying to move up as well. They start colliding right through here to give us the Ring of Fire, which is all of those volcanoes that line from here all the way up. And I say this is the Pacific plate, which continues over here to give us the ring of volcanoes that we have. What happens here is that the Pacific plate is in the ocean. Therefore, it is more dense. So it sinks beneath the continental plate, the Eurasian plate right here. So the Eurasian plate rises up to give us a bunch of different volcanoes. Same thing over here. The Pacific plate right through here is sinking, and the Nazca plate is sinking. It is subducting, while the South American plate is rising up because it's continental, it's less dense, to give us mountains and volcanoes.
When we least expect it, when we're least prepared, disaster can strike. And few disasters are as unsettling as an earthquake.
So it's important to
My guess is that earthquakes are really so scary because you don't have any warning. It's the only thing besides a nuclear war that can really, 1 second you're living in a big beautiful city, and 10 seconds later it's flat.
Every day the earth is shaken by hundreds of small earthquakes. Most go unnoticed. They usually occur along the boundaries of the thin plates that cover the earth like an eggshell. Driven by the heat deep within the Earth's core, the plates grind against each other on long lines called faults. When the plates find their motion blocked, stress builds up. Finally, the fault gives way. The released energy races through the Earth in the form of seismic waves. For much of the world, the movement of plates like these is also an indispensable creative force.
If we didn't have earthquakes, if we didn't have this great flow of heat from the interior of the Earth would be a cold, dead place. If it wasn't for this great flow of heat, there'd be no continents, no oceans, no atmospheres. The Earth would be as dead and dry and cold as the moon. It's really the earthquakes that create the topography, the valleys, the mountains.
Earthquakes have been shaping landscapes for eons. It's only in the last few hundred years that civilization has gotten in the way. And when it does...
This is just an excerpt from Nature's Fury. The full video is available at nationalgeographic.com.
So whenever we're looking at this, we need to understand that every time those tectonic plates build up stress and they slide and slip, that's whenever we have an earthquake. Now, earthquakes can occur in 3 different ways. They can occur at a convergent boundary where they are coming together. They can occur at a divergent boundary where they are separating, or a transform boundary where they are sliding past one another. Whenever we have earthquakes, we measure their movement, which is their vibrations, on a scale. The scale is called the Richter scale. These vibrations we call seismic waves, which are also known as earthquake waves. This is a picture of how much damage an earthquake could occur and could cause if we had one here. Now, this is over in Japan. But you can see as they crumbled how it just fell off and fell down into the earth.
Just like California, where most Americans may think all our earthquakes are centered. But California's San Andreas is just one fault zone. There are at least 4 active earthquake zones that cover this country, all of which seismologists say have had historic eruptions, and each could have another catastrophic strike at any time.
Earthquakes are a national hazard, and it's in these areas away from California, away from the places we think about, where there can be some of the greatest risk.
What about America's heartland? We're on the 2nd most active fault in the country, and that's the New Madrid Fault. It runs from St. Louis to Memphis, and this is Reelfoot Lake, 16 miles long, and created 200 years ago by what is still today the most powerful series of earthquakes in American history. It happened nearly 200 years ago on the morning of December 16th, 1811. An estimated 7.5 on the Richter scale. It was followed by a series of 2,000 aftershocks. Over the next 5 months, some measuring 8.0 and felt as far away as Boston. New Madrid is the biggest fault line east of the Rockies. It extends 120 miles through 5 states, cuts across the Mississippi River in 3 places, and slices the Ohio River in half. Even now, the area averages a tremor every other day. A major earthquake here would affect 15 million people in 7 different states.
Do we think there's a big earthquake on the way for this zone?
Yes, we have a history of large earthquakes that have occurred here, at least over the last 1,500 years, about every 500 years. And those earthquakes occur as large sequences of events, not just a main shock.
New York, New Jersey, and Pennsylvania have the 70-mile-long Ramapo Fault. These streaks are really all that's visible of the Ramapo Fault, and they continue all the way up this rock. It's one of the largest in the Northeast, and we're really just about an hour outside of New York. Never heard of it? Well, it's been quiet for a couple of hundred years, and seismologists say that's part of the problem.
We know that in the future, at some point, an earthquake is going to occur. But we don't really understand the rules of the game yet in this area.
What we do know is the last major activity on the Ramapo Fault was a 5.2 centered in Brooklyn, New York in 1884. And if that same quake hit today, there are now 8 million residents of New York City. All could be affected by the Ramapo Fault's dangerous reach.
One important fault is the one that crosses Manhattan from the Hudson River to the East River, more or less along 125th Street. That's a well-known fault. There are tunnels constructed for the water and for the subway lines underneath that cross this fault.
And of course, there are 2 other hotspots. One, a subsidence zone that's just off the Pacific Northwest coast. It's in the water, but it's pretty active all the time. And the granddaddy of them all is the San Andreas Fault. There are thousands of earthquakes there every year.
So whenever we're looking at earthquakes, we need to know that the most damage that we have of earthquakes are caused by surface waves. A surface wave is whenever the focus, the actual location of the earthquake is closer to the surface of the earth than it is within deep into the earth. Now, unlike deep focus earthquakes, a focus is where it occurs, where the actual snapping effect occurs. Surface waves occur at all type of plate boundaries. So the question is, what could a surface wave cause for those living near the seashore? So if we have a wave near the seashore, we call this a seismic sea wave, which is also called a tsunami. Since we're talking about seismic waves and tsunamis and the focus of where they occur, we need to understand why certain waves are faster than others, why certain earthquakes cause more damage than others. It's all due to seismic wave speed and densities. Seismic wave speed is affected, so our earthquake speed, the damaging effects of the speed, is affected by the density of the material that it actually moves through. So you'll need to get a sheet of paper and draw this diagram, and I've even numbered our little molecules in here so we can see what's going on. So first of all, this top layer, remember this is your crust, this is your upper mantle, these two create our lithosphere, and this is our asthenosphere right here. As we go down to the core, we increase our density. The way that we're showing that, you see that these molecules are really far apart. As we go down here, they start getting closer together. So what happens is, if we have an earthquake that occurs way up here, this is less dense. So it takes a really long time for this molecule to go and hit and consistently bump off of each other. The slower the speed of the earthquake, the more damaging it is. Now, if we have an earthquake that occurs right here, this is more dense, so it's not as much space between each molecule to bounce off of each other. So it'll bounce really fast, which means it'll go through really fast and not cause as much damage. So this is more dense and fast. This is what we see for the Ring of Fire. This was what's in the book, almost. The Ring of Fire, we have our Pacific plate right here. That is, remember, it is more dense because it's an oceanic plate that converges right through here. It converges with your continental crust this way to give you a ring, an actual ring of volcanoes. 90%, almost all of the earthquakes that we have in America and in the entire world occur somewhere along the Ring of Fire. See, we have Japan over here. We have California right over here. All of these, where they have actual earthquakes, occur because the Pacific plate is more dense, so it sinks in response to colliding with the continental plate.
堤防を越えます今。船も堤防を越えるかもしれない。
So now that what you saw was an earthquake. It occurred under the water to create our tsunamis. Now, if you remember in the video, you saw mountains in the background. That was a convergent boundary. When they converged, the oceanic plate subducted, the continental plate peaked up to build upon the mountain, but that snapping effect of it peaking created vibrations, created seismic vibrations in the earth. These vibrations were transferred to the water, which then created the tsunami over in Japan. Now, something really cool about earthquakes is that animals are in tune to when an earthquake will occur. They are more prone to feeling vibrations of the earth than we are as humans. So they'll start to act funny. In some locations, they'll actually jump out of the water in response to feeling any form of vibration in the water or under the ground. Birds can feel it in the air even, and they'll fly and flock away from the location where the vibrations are. Same thing with mice and bugs and all these. They will scatter, they'll run away. Rats begin to panic. Horses will refuse to eat or enter the barn, feeling the vibrations. Birds, which usually stay in trees, will suddenly fly away from the trees. Goldfish will swim around frantically. Deer and rabbits run away from the epicenter, which is the center of where it actually begins under the earth, under the crust. And fish in freshwater, whenever they feel it occurring, like right here, will jump wildly up and down in response to these vibrations. Now this is a picture and a video of a bridge that was actually built to accommodate these seismic vibrations, these earthquakes. It was built to be able to spin in response to the vibrations of the ground. As the ground shook, it was able to spin and move as well. The only problem with that is eventually they give way when they're built to be able to move like this. Bad enough of an earthquake, it will eventually crack the cement and it'll cave in, which is what eventually happened here. Now this invention was brilliant and was state of the art at its time. However, once it did fall and collide, they were easily able to realize that it's not always best. What happened was this bridge was built extremely narrow, so it was able to wiggle. But the problem with the narrowness of the bridge was that when it did wiggle, since it was so small, it easily crumbled into pieces.